For your final project this year, our goal will be to perform a test on this bridge on campus in UW-Madison. It's called the Alicia Ashman Overpass. Um, Most of us just know it as the Wobbly Bridge over by Babcock. And our goal will be to perform a test to measure the natural frequencies and mode shapes and understand why the bridge wobbles. So a little more detail. Oh, by the way, everything we're doing is building on a project in 2013 when some students did a test on the bridge. They managed to measure some of the natural frequencies, but there were some problems that didn't allow them to measure the mode shapes and to really thoroughly validate the model that they got. So we're hoping we can do better this time. So anyway, the overpass apparently was named after an alderman, Alicia Ashman, built in 1977, so it's a relatively young bridge, and about 180 feet span, that arch, so pretty large bridge, 10 foot wide. But it's, as you know, it's fairly thin and light and flexible. You can see here there's two arches going on. It's a suspension bridge, so this arch carries the weight of the bridge, and the deck is also arched slightly. So one reason that we're doing the test is to try to understand why the bridge feels so wobbly when you walk on it. This was studied as part of a civil engineering project. They actually created a model and simulated the marching band going over the bridge to see if the bridge would be safe in kind of an extreme case like that. There's some detailed drawings where you can get some more information on the bridge, on the design and how it's built. So basically, again, an arch suspension section over the road. Once you get over the road, there's this spiraling ramp that brings you back to ground level. And you can see the detail on that here. And we're given a model that was created by this civil engineering class that predicts the natural frequencies and the mode shape. So it gives us an idea of what we can expect when we're testing. And you know, there are times that we do tests not knowing anything, not knowing what we're getting into, but usually when a big test is done, there's some kind of model that will guide the results. Or if not, maybe we'd have an idea of what we think the results might be, and we'd use that to guide us. In any event, here's the model. And I solved that model in a program called SAP, a finite element program that civil engineers like, and calculated the different bending modes of the bridge. So this first bending mode has the deck kind of doing an S shape. You really do feel this mode a lot as you walk on the bridge. You'll notice if you stand in the middle, the bridge feels quite stiff. If you're out on these parts, you can feel it moving up and down. So that's the first mode around 2 Hertz. The second mode, side-to-side swaying, you can see that better here. And so if we want to capture this mode, we're going to need some sensors up a little higher on the bridge. You'll see that in the plan, because there isn't a lot of up and down motion in this mode. Mode 3 is, again, kind of torsion of the top part of the bridge, but actually the main thing happening is over here. This is the first mode of the ramp. And I guess you could think of this as a cantilever mode of the ramp rocking like this on the pillars that support it. And this is important, these sets of modes, because we suspect that some of the biggest problems in the existing finite element model have to do with the connection between this part and this part. There's an expansion joint here that's tricky to model. And this part is especially wobbly. So we'll pay attention to that. The next mode seems to be kind of a higher order torsion, maybe with some extra motion of the deck. Here we're really starting to wonder how accurate the model might be. We're only at 2.8 Hertz at this point. And then the even higher modes, 5 and 6, seem like a higher order kind of a torsion or lateral bending of the bridge, with different amounts of deck involved. 7 and 8 are where we get to see some of the higher order bending modes of the bridge. So here this one has kind of a 3-hump bending mode. So our goal is to measure these modes so we can get an idea of how accurate the finite element model might be, where it might need corrections. This is just a summary of all the natural frequencies, 8 modes below 4 Hertz. And so that's mostly where we'll focus our attention. Okay, so because of where this lands in the course, I'm going to just give you the design for the test. And we'll talk later about how this is done, and you'll get to see about designing a test. But basically, I defined a grid of measurement points, the 100 sensors along this edge, the 200 sensors along the back edge, and then a 300 series along the ramp, starting from this point. We also, in case we are able, defining another set of sensors, 151 or 152 through 166. And these points are similar to the edge here, but they're up as far as we can reach, assuming we're not going to have a ladder or a lift or anything available. So they're up as far as we can reach and hopefully can catch that torsion and sway of the bridge if the other sensors can't. Okay, so those are all the points we want to measure, but we only have a limited amount of hardware available. So what we're going to do is we're going to move around the hardware that we have. First, I've picked a set of locations that I think we always want to be watching. So that's these 2 points on the bridge in the vertical direction, 1 point laterally on the ground, and then another point in that 150 series up as high as we can get. So we always want to be watching that so we can tell whether the bridge is moving. And then a set of sensors on the ramp. I said the ramp motion was important, so we'll watch that always so we can see the connection between the ramp and the rest of the bridge. So we'll have a 4-channel box going to each of these spots and measuring in each of those sensors. Assuming our cables are long enough, we'll adjust when we get there if we have to. Okay, and then everything else will be measured by these roving setups. So we have 2 other boxes left, 8 other sensors. So for the first test, we'll put 4 sensors here, 4 sensors there. And we'll try to measure those points. And if all goes well, we should be able to capture all of those in one setup, and that will provide some detail to the mode shapes we're trying to measure. A second setup will basically just take these sensors and shift them over. So now we should have a pretty good picture of what the mode shape looks like through here. And then in a third setup, we'll finish out what we're doing, grab a few more points on the bridge, and then grab a few more points on the ramp there. Okay, so that's the plan. We'll have paper, we'll have cameras to document in case we do anything different. And I've also even written what order we'll put all of these in the different boxes so that we can hopefully keep all of the labeling consistent. Okay, and what we'll do is be measuring the response of the bridge just to operational forces, or basically a few people just walking around. Maybe we can have some jumping and things as well if we want to simulate more of an impulse. But just normal walking or jogging on the bridge should be enough to get enough motion that we can measure and see what's happening. We'll measure up to at least 25 hertz, though again, most of the modes we're interested in are down below about 5 or 10 hertz. And that's basically the plan. So each of you will be showing up in teams and be helping for a little bit. A couple things to think about whenever we do a test like this. One key thing is we always seem to never take good enough notes about what we were doing. So as you're there, we'll encourage you, use your cell phones or whatever camera you have. Take lots of pictures, all the different hardware, where the sensors are, what that looks like, so that we can hopefully reconstruct if we get any mysteries when we get the data back. And yeah, be ready to learn about operational modal analysis and collect some data. And then we'll have quite a bit of time for you to learn some of the data analysis techniques and things that we'll use to make sense of it. All right, we will see you in the test.